Getting a robot to do really delicate, precise tasks like slotting a battery into a device or threading a tiny Velcro tie, that's one of the toughest challenges in all of robotics. So today, we're going to do a deep dive into ACT, a really powerful imitation learning algorithm that's designed to teach robots these exact kinds of complex, fine-grained skills, just by watching a human do it first. Here's the plan. We'll kick things off by looking at the core challenge of just trying to copy a human. Then we'll break down the two key innovations that make ACT so darn effective, action chunking and its unique architecture. And finally, we'll see how it all comes together in the real world. All right, so the most straightforward way to teach a robot something is just to have it watch you and learn, right? Well, this approach is called behavioral cloning, but as we're about to see, it has some pretty fundamental weaknesses. Weaknesses that ACT was specifically built to fix. At its heart, behavioral cloning, or BC for short, seems really simple. The policy, which is basically the robot's brain, it watches an expert and tries to learn a direct mapping. When you see this, do that exact thing. Think of it like learning to drive by trying to perfectly copy a pro racer's every single steering wheel turn and pedal press, moment by moment. The problem is, this method can be incredibly brittle. And that leads us right into the first major failure mode, compounding errors. Even a tiny, almost unnoticeable mistake in one single step can put the robot in a slightly different situation. The next mistake pushes it a little further away, and pretty soon, these tiny errors snowball. The robot finds itself in a situation it has never seen in its training data, and it has absolutely no idea how to recover. This is a classic problem in imitation learning called covariate shift. The second huge challenge is what we call the multimodality trap. So imagine a human shows a robot how to grasp an object. In one demo, they grab it from the left. In the next, they grab it from the right. Both ways are perfectly fine, totally valid. But a simple learning algorithm might try to average those two demonstrations and learn to go straight down the middle, a move that's guaranteed to fail by crashing right into the object. It literally averages two good solutions into one really bad one. So this brings up the big question, doesn't it? How can we possibly build a policy that doesn't get lost because of tiny errors, but can also handle the fact that there's often more than one right way to do something? Well, this is exactly where Actia's innovations come into play. ACT's first brilliant solution is all about tackling that compounding error problem head-on. Instead of having the robot think one tiny step at a time, it forces it to think in short sequences, or what it calls chunks. This really helps make sure its movements make sense over a period of time, which stops it from slowly drifting off course. This slide really shows the key shift in thinking. Standard behavioral cloning, on the left, looks at the current situation and predicts only the very next action. That's it. But ACT, on the right, looks at the same situation and predicts a whole sequence of actions for the next K steps, an action chunk. The seemingly simple change forces the model to learn motions that are coherent over time, and that dramatically improves its consistency and cuts down on those cascading errors. Now, action chunking is a fantastic idea, but you need the right kind of neural network, the right brain, really, to make it work. And that brings us to ACT's second key solution, which cleverly combines two really powerful deep learning models. The ACT model is built on what's called a conditional variational autoencoder, or CVAE, and a transformer. The CVAE is there specifically to solve that multimodality problem we talked about, the whole left grasp versus right grasp thing. Meanwhile, the transformer is just amazing at taking all the different sensory information the robot is getting and fusing it all together. So how does the CVAE actually solve the multimodality trap? Well, it introduces a special variable called a latent variable, which you can just think of as a style or mode variable. During training, this variable learns to represent all the different valid ways a task can be done. So when it's time for the robot to act, the model can just commit to one style, like the left side grasp, and then generate a whole sequence of actions that are consistent with that one choice, instead of messing things up by averaging all the styles it's ever seen. And this is where the transformer comes in. A robot isn't just looking through one eye, right? In this case, it actually has 4 different camera views, front, top, and one on each wrist, plus its own internal sense of its body position, which is called proprioception. The transformer's attention mechanism is basically purpose-built to intelligently weigh and fuse all of this information together to get a really complete picture of what's going on before it decides on an action chunk. Okay, so we've covered the core ideas behind ACT. Now let's take a quick look at how a model is actually trained up and then used to control the robot in the real world. The training process is actually pretty elegant. First, the model just grabs a batch of data from the human demonstrations, which includes what the robot saw and the sequence of actions the human took. Second, the CVAE encoder looks at that human's action chunk and kind of boils it down into that single style variable z. And finally, the transformer decoder uses what the robot sees and that style variable z to try and perfectly reconstruct the original action chunk. The model just keeps getting better and better by minimizing the difference between its prediction and what the human actually did. Now, the inference step, what the robot does when it's live, this is where things get really, really clever. Okay, so at every single time step, the robot predicts a brand new action chunk. This means it's constantly replanning its next few moves. But here's the magic trick. Instead of just using the first action and throwing the rest away, it uses a process called temporal ensembling. It takes the predictions for the exact same future moment from all the recent, overlapping chunks that is predicted, and it smoothly averages them together. This constant cycle of replanning and smoothing is what gives the final robot motion its incredible precision and stability. So let's just put it all together. ACT provides these specific, targeted solutions to classic problems in imitation learning. The whole compounding errors issue, that's solved by thinking in action chunks and then smoothing them out with temporal assembling. And the multimodality trap, that's solved by the CVAE architecture, which lets the model commit to a single, consistent strategy instead of incorrectly averaging everything together. ACT is a massive step forward for what we call predictive models, policies that learn to precisely imitate what they're shown. I mean, it seriously outperforms older methods. We're talking success rates of 88% on opening a Ziploc bag and 96% on slotting a battery on tasks where other methods completely failed. This kind of success really paves the way for the next big frontier, generative policies. Because the ultimate goal isn't just to have a robot that can copy a human perfectly, but for a robot to be able to generate entirely new, creative solutions to problems it has never even seen before. So what do you think is the key missing piece to bridge that gap from just imitation to true robotic creativity?